All right, so we continue here. We saw the three saccharides, three monosaccharides. That's the glucose, fructose, and galactose. And we also discussed how different the glucose is from the galactose. So let us continue from here. These are just the simple carbohydrates. So when you think about carbohydrates and you talk about connectivity, here we have carbon, so they make this ring here, 1, 2, 3, 4, 5, 6 membered ring, but one of the carbons is replaced by oxygen. And then we have the OH, and we have OH here. So you can see, if you count, you see that oxygen to hydrogen is 2 to 1. We have 1, 2, 3, 4, 5, 6 oxygen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. So that is 2 to 1. This is a monosaccharide, and this is glucose. Now, when you add two monosaccharides, you see what you are doing? You're getting rid of this water molecule here. When you add two monosaccharides, they give you a disaccharide. In this case, when you add glucose, let me just plus glucose, it gives you the maltose. So if you combine two glucose molecules, they give you this maltose molecule. But as you have seen, the process is dehydration. So what you are doing in dehydration, you get rid of this water molecule and you get rid of this hydrogen. Once you do that, you have remaining with a hydrogen here, and since you get rid of something here, this one will be, there will be a positive because you have removed the whole thing. You have removed this whole thing with its electrons, and you have a positive remaining here. When you remove hydrogen here, you are going to have H or with a negative, and then you have that. So this negative here will connect with this positive down here to make that one. So that's what hydration is. But now, because you have removed hydrogen from here, and also you have removed OH from here, they combine to form water. That's the water you are seeing here. So this process, the synthesis of maltose, is a dehydration process because we have removed water from these two molecules. So that synthesis is the same as making. That's what synthesis means. Synthesis means you are combining to make something. So I'll define that. Synthesis, combining to make something. So you are combining things to make something. Here we are combining glucose and glucose to make maltose. Glucose is a monosaccharide, the other glucose is a monosaccharide, the maltose is a disaccharide. So this is what we are saying. One OH gone, one hydrogen gone, and then these form water, and then we have our connection, dehydration process. That is making disaccharides and polysaccharides. The way we are making this disaccharide is the same way that we will make a polysaccharide, because it will continue this side all the way and make a polymer. So in this case, this is a monomer. This one is also the second monomer. So the disaccharide is a dimer. A dimer has two monomers. So dimer has two monomers, while polymer has so many monomers. So polysaccharides are the large polymers of monosaccharides. So what is a polysaccharide? Polysaccharide is large polymers of monosaccharides. One example of a polysaccharide is cellulose. So cellulose is used for structures in plants, right? E.g. gonje. Maona gonje mukapanga amasala ndi zingwe zija. Zingwe zimene ni polymer ameneyo. So cellulose is a polymer that is used as a structural carbohydrate in plants to make the plants rigid, or to support the plant. We use cellulose. Also, it is used as fibers, like gonje fiber. And also, when you are saying I'm eating fibers, you are thinking about these polymers. Normally, fibers, you cannot digest them. That's a problem, so you need to be careful. They are indigestible by human enzymes. So take note of that. So this is polysaccharide number 1. Like, how many polysaccharides do we have? We have cellulose. Polysaccharide number 2 is starches and glycogen. So these, we use them to store energy. We don't store energy using polymers. Reason is because polymers are indigestible. So do not store energy here. We do not store energy because they are indigestible. So which means they will not undergo respiration to make energy. That's what it means when we say they are indigestible. I don't know why the color of my pen went back to. Starches are quick energy storage. So these ones are digestible. So you can store energy in them, which implies can store and release energy. Through respiration, while the cellulose will not do that. Now, what is the difference between a starch? the difference between a starch and glycogen. So I think you'll be asked that in your quizzes. What is the difference between starches and glycogen? The difference is that starches are long chains of glucose in plant cells. So really, where you find starches are in plant cells, but also they are long chains. While glycogen is found in animal. It's called animal starch. It is also composed of long chains. It is made of long chains of glucose. So starch is found in plants, while glycogen is found in animals. So that's one big difference. The big difference is where they are found. Starch deals with energy, but in plants. Glycogen deals with energy, but in animals. So this one, what we are seeing here, this diagram is a cellulose. Let me just get rid of. Just let me erase that part. So the diagram you see here is cellulose. Now look at the cellulose. Cellulose, look at this. If you want to identify that this is cellulose, that's very important, because you can be given a diagram and say, is this starch? Is this cellulose? In cellulose, we have you see, these ones, they look like that. So the oxygen is the connecting oxygen is in a zigzag position. So I can say in cellulose, the connecting oxygen are trans. Trans just means across. Across to each other. They are trans to each other. So what does it mean? You see, this and this. This and this. They are in a zigzag position. So take note of that. So, and if you are given a leaf, you see this part of a leaf, these ones are cellulose. This here, this is cellulose. This one is cellulose. They provide support to this leaf. Cellulose. All these are cellulose. But the issue is when you look at it, you see here, it points up, here it points down. Here it points up, here it points down. Here it points up, here it will point down. So the structure, the connecting oxygens are in a zigzag position, or are trans to each other. That is cellulose. Now, when you go to starches and oxygen, you see that the connecting oxygens are on the same side. So starches and glycogen, the link or connecting oxygen the links or connecting oxygens are on the same side. So you can see here, both of them are just pointing up, right? Both of them are just pointing up. So this one is starch, found in plants. Now, how is it different from this one? This one is glycogen. Found in animals. Glycogen is different also from starch because glycogen has more branches than starch. So you can see here, it is showing us a branch. We are moving here, we are branching here, but the other is continuing. While for starch, it's just a straight line, no branches. So that's the difference, another difference between glycogen and starch. As you can see, this one is a glycogen. You can see the branches here, right? Take note of the branches. That's glycogen. Glycogen has a lot of branching. It has junctions, or I say junctions. While starch is just a straight line. So starch lacks branching. It will just start from here all the way. But in terms of the connecting hydrogens or the connections, they are one side in both cases. So there are two differences between starch and glycogen. One differences between starch and glycogen. The first difference is starch found in plants, glycogen found in animals. That's the first difference. The second difference, glycogen is more branched than starch. Similarities between the two: both are made of glucose polymer or glucose monomers. That is one similarity. The connections also are on one side. The second similarity. Connections or connecting oxygen is on one side. Connecting oxygen is on one or same side throughout the molecule. Is on same side throughout throughout the molecule. I don't think throughout, I'm going to behind you. Through. Okay, yeah, but it's throughout the molecule. So that's the difference between, or the similarity between glycogen and starch. Now let's move on to lipids. When we talk about lipids, we are talking about several things. Lipids is not just one thing. And lipids is not a monomer. It is not a polymer. It's just a big molecule. That's all. So lipid is not a polymer. It is a big molecule. So when we talk about lipids, if I ask you, can you give me examples of lipids? Lipids has a lot of things. It has fats, it has oils, it has what we call steroids, waxes, and phospholipids. All these are examples of lipids. So these are examples of lipids. Lipids are non-polar. What it means is they will not dissolve in water. So the lipids will not dissolve in water. What you will see is they are going to either float or go below the water. We don't see them mixing with the water. So they are insoluble. They do not mix with water. That's what it means. Because the reason is lipids are non-polar. What does non-polar mean? Non-polar mean they don't have separation of charges. So non-polar. Non-polar means no separation of charges. That's what it means. Let's take water. Water is written as OHH. This part is partial positive, this part is partial negative. So there is separation of charges here. Because of that, water is polar. Lipids do not have separation of charges. Therefore, they are non-polar. And things that are non-polar are not going to dissolve in water. That's what it means. Things that are non-polar are not going to dissolve in water. So you need to write down that. So what is their function? Fats also contains calories of energy. They are also energy storage. We talked about carbohydrates as energy storage. Fats are also energy storage. So they do work like carbohydrates. But then fats actually store more energy than carbohydrates. Right? That's why they are dangerous. So store more energy than carbs. So sometimes also they also help with structure, like we see with cellulose. So they also function as structural components, but mostly we use them for insulation. People in Alaska have a lot of fat to insulate them from the cold. It's very cold there. You need a layer in your body, a layer of fat that can insulate you from the cold. Also in the body, you need some layer of fat to cushion organs and hormones. So you need a layer of fat to cushion organisms. Some fats also work as hormones. So the function of fats, we have several of them. 1, to store energy. 2, it is a structural component. 3, we use them for insulation. 4, we use them to cushion organs. 5, they are used as hormones. So you need to write down all these 5 functions of fats. I am going to ask you about that. So one important molecule that we have for fats is a fatty acid. So what is this fatty acid? Fatty acid, I think, is a very important molecule of the lipid section. So a fatty acid has this part. This is a functional group that we saw last time. It is a carboxylic acid. So because of the presence of the carboxylic acid, we call these fatty acids. They are acids that have fat in them. So if a fatty acid would be a long chain, as you can see here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 carbons, and this one 12 one, will be a longer chain, but at the end of that chain, there is a carboxylic acid. So a fatty acid is a long carbon chain with a carboxylic acid at the end of the chain. That's what a fatty acid is. And you can see the chain itself. This part is a hydrocarbon chain. So it's a long hydrocarbon chain. Hydrocarbon means having carbon and hydrogen only. That's what hydrocarbon means. So you can see this is a long chain of hydrocarbon, and then we have a carboxyl group or carboxylic acid group towards the end of the chain. So as we'll see later, what happens, you see this chain here, or this carboxylic group, we can cut this part and connect it to something. That's what happened here. So we added this chain. We added this chain here. We added this chain here. We added this chain here to make a lipid. So a lipid made from fatty acids. And also take note of one thing. Count the number of double bonds here. We have 1, 2, 3, 4, 5. As you increase double bonds on a fatty acid, the lipid becomes liquid. So sunflower oil is liquid. Sunflower oil is liquid because the fatty acid chain has 5 double bonds. So here we talked about a fatty acid chain here, but here you can see we have 3 of them. Chain number 1, chain number 2, and chain number 3. When we combine these with this part we call it a glycerol or glycerol. That's where we make glycerin. We call it glycerol. When you combine glycerol and fatty acids, you have your lipid there. And the lipid will be in liquid form if you have so many double bonds. So sunflower is a liquid. The same with canola oil. You can see we have also 5 double bonds here. We expect canola oil also to be liquid, and you know how canola oil looks like. It is a lipid, but it is in liquid form. Now look at margarine. Margarine only has 2 double bonds. So the fewer the double bonds, the fewer the double bond the more solid the fat, or I'll just say lipid, the fat is. This one has only 2 double bonds. You see now, it's solid. That's the structure of margarine. Only 2 double bonds, it is a solid. When you reduce the number of double bonds, you are increasing the solid nature of your fatty acid or of your lipid. So all these are fatty acids. You can see they have fatty acid chain. Chain 1, chain 2, chain 3. So we are talking about fatty acids that are liquid and fatty acids that are solids. So we define them in 2 ways: fats and oils. So oils are liquid at room temperature. Oils come from plants. So if a fat, if something is coming, if a lipid is coming from peanut, it will be an oil because it comes from plants. So e.g. sunflower oil, peanut oil, I don't know, canola, I think, yeah, canola oil, and all these other oils that you see in liquid forms, they come from plants. While fats are solids at room temperature and usually come from animal origin. So when you think about margarine, think about it coming from animal origin. So like margarine, nyama indi mafuta, that is fat, and we see that mafuta they are solids. So fats are called triglycerides. So they are composed of a glycerol and 3 fatty acids. That's what I was showing you, that each one has 3 chains. Chain 1, chain 2, chain 3. So we'll show you where how these are formed. But also just take note that in terms of energy, fats are very important for energy storage and insulation. If you are going to cold climates, you need to have a lot of fat. Otherwise, now, what happens is we have these 3 fatty acids: chain 1, chain 2, chain 3. 3 chains. Then we have a molecule that is known as glycerol. This molecule has these 3, the OH, as you can see here. The fatty acids also has OH. So what happens is the fatty acid itself is going to lose this OH. This is a dehydration process again. While this one loses 1 hydrogen here. So this dehydration process is we are going to lose 3 waters. This is 1 water, 2 waters, 3 waters, to form what we call a fat, that is triglyceride, which means this glycerol we have added 3 fats to the glycerol. That's why we call it triglycerol. Or we have added three fatty acids to a glycerol. That's why we call it a triglyceride. So you can see that we have 3 chains: chain 1, chain 2, chain 3. This is what we call our fat, or a triglyceride. So a triglyceride is formed through dehydration. So let's take note of that. Triglyceride is formed through dehydration, like the same case when we form carbohydrates. But even if you want to destroy the triglyceride, you use hydrolysis. So you can destroy triglyceride through hydrolysis. Like we saw that you can destroy a polymer through hydrolysis to make monomers. So take note of this reaction. You can be given reaction, say, oh, pointing this direction, what do we have? We have dehydration. Coming back to this direction, what do we have? We have hydrolysis. That is the formation or destruction of fats from triglycerides, or from a glycerol or glycerol and fatty acids. So this is the synthesis and degradation of a fat molecule. So what do liquids do, or what do fats do? Fats undergo emulsification when you put them in water. Because they are not polar, they will not dissolve in water, so they will form globules. So when you put these globules are like the small droplets. We see the small droplets we see when we put oil in water. So the globules are what will happen is the oil is separated from each other, or drops of oil are separated from each other. So drops of oil are separated from each other and are dispersed throughout the water. So that is emulsification. So I'll stop here and continue with the video later.